Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all to the class of real analysis. In today's lecture, we are going to discuss two important topics. One is completeness property of R, and the second one is complete ordered field. So far, we have discussed about concept of supremum, infimum, upper bounds, lower bounds, and bounded sets. I hope you have a clear understanding about these concepts. So, in the completeness property of R, we will discuss two important properties. First is the supremum property. Supremum property can be stated as every non-empty subset of real numbers which has an upper bound has the supremum in R. If you have any non-empty subset of R which is bounded above, mean to say which has an upper bound, then the supremum's property says that it must have supremum, and that supremum will exist in R. For example, if you have a subset of R that consists on first 20 natural numbers 1, 2, 3 up to some 20, you can see that this set is clearly subset of real numbers R. Now all the numbers which are greater than 20 or itself 20 are the upper bounds of set A. The least upper bound of set A, that is actually supremum of A, which is equal to 20, and this 20 also belong to set R. So this set A fulfill the condition of supremum property. The second one is the infimum property. With a similar manner, we can define infimum property as every non-empty subset of real numbers which has a lower bound. In the supremum property, we discuss about the upper bound. In the infimum property, we discuss about the lower bounds. So every non-empty subset of R which has a lower bound has the infimum, and that infimum must exist in R. Again, from this example, we can see that this set A is bounded below because every real number that is less than equal to 1 is the lower bound of A. For example, 1 and all the real number which are less than 1 are all the lower bound of A. Like as 0.5 is also lower bound of A, 0.25 is lower bound of A, 0.80 is lower bound of A, minus 100 is lower bound of A. So this set A is bounded below. Now the infimum property says that if a subset, if a non-empty subset of R which has lower bound, that set must have infimum in R. So you can see that the set A has the infimum that is equal to 1, and this one belong to R. This is the infimum property. Both property can be summarized as or can be combined as every non-empty bounded subset of real numbers. Here the term bounded subset of real number means a set is called bounded set if it is bounded above as well as bounded below, is called bounded. So every non-empty bounded subset of real numbers has the supremum and infimum in R. Next we move to the complete ordered field. An ordered field is called complete ordered field if it satisfies the completeness property. This is the simple definition. An ordered field is called complete ordered field if it satisfies completeness property. In the completeness property, it is sufficient to state that of an ordered field is called complete ordered field if it satisfied only supremum property. Because if a field satisfies supremum property, then it must satisfy the infimum property. So in the numerical question, when we will show that a certain given field is an complete ordered field, then it is sufficient to show that that ordered field only satisfies the supremum property. There is no need to check whether it satisfies infimum property also or not. So the complete ordered field can be defined as an ordered field F. An ordered field F is called complete ordered field if it satisfies supremum property. What is the supremum property? That is every non-empty subset of F that is bounded above has the supremum in F. It is important to note that if a field satisfies supremum property, then it must satisfy infimum property also. In our previous discussion, we have discussed that both Q, set of rational numbers, and R, set of real numbers, both are the ordered field. Now, as we have learned that R satisfies completeness property, so R is one of the complete ordered field. But on the other hand, Q is not complete ordered field because there are many subsets of Q that are bounded above but has a no supremum in Q. For example, if you observe a very important subset of Q, like as suppose the set name is J, X such that X belong to Q. Q means set of rational number, and X is positive, mean to say this is a set of positive rational number that satisfies the condition, and X square is greater than 2. Now every number, if we solve this inequality, X square greater than 2, where X is positive, this will give us X greater than square root 2 by taking square root on both sides. Now every real number, every number that is greater than or equal to under root 2 is upper bound of this set J. But the least one, the least upper bound is square root 2. So the supremum of J is equal to square root 2. But you know, square root 2 is an irrational number, and this irrational number does not belong to Q, because this is a rational number and Q is set of rational number. So we can see that this is, although a subset of Q, clearly this is a subset of Q, and this is also a bounded above set because its upper bound exists. Any number, there are many rational numbers which are greater than square root 2. Square root 2 is approximately 1.41. Now all the numbers which are greater than 1.41 are all its upper bounds, like as 1.5, 1.51, 1.62, etc. These are all the upper bounds of this set J. So there are many rational numbers that are the upper bound of J. So the J is bounded above subset of Q, but the least upper bound of J is square root 2. That is an irrational number, and this irrational number does not belong to Q. So Q is not a complete ordered field. So in the next lecture, we will discuss, we will prove properly that Q is not an irrational number. In today's lecture, we have only discussed about the concept of complete ordered field and the completeness property of R. I hope today's lecture is helpful for you, and now you have a clear understanding about today's topics. Inshallah, in the next lecture, we will discuss about the completeness of Q. Okay, take care. Allah Hafiz.